Hey class, so this is our lecture regarding the countercurrent heat exchanger. We're still on the topic of heat exchanger. So last week we finished the discussion on parallel heat exchanger. But before we start, I would like to acknowledge the author of the slides. These slides were made by Dr. Monette Detras, and I'm just adapting it for our discussion. So again, for a countercurrent heat exchanger, as you can see, the direction of the hot fluid and the direction of the working fluid and the hot flue gas are in the opposite direction. So for example, for the hot flue gas, it entered this side of the heat exchanger, then the cold fluid would enter at the opposite. So it's what you call countercurrent heat exchanger. For the temperature profile, this is what it looks like, uh, but in graphical form, it would look like this. So our goal in the calculation for countercurrent heat exchanger would be to construct this graph. Okay. So this is a temperature versus sensible heat plot. And again, the small letter t would correspond to by convention, we assign that to the working fluid, and the capital letter T, we assign that to the flue gas. So we have the flue gas line and we have the working fluid line. So using the same problem that we solved last time, we will resolve it, but this time assuming a countercurrent heat exchanger. So just like the first problem, our first step would be assuming arbitrarily any T. Okay. So for the flue gas stream, our flue gas enters the heat exchanger at 1500 degrees Fahrenheit. So it would be best to assume values less than this temperature. So we just do the same with the working fluid. We also assume different temperatures. So this would depend on you. Okay. Okay, the next step would be, since our reference temperature is 60, and we actually made the temperature of the cold fluid or working fluid, which is air, so it's 60 degrees Fahrenheit, we also set that as our reference temperature. So we just subtract the reference temperature with the arbitrary values of temperatures that we came up with earlier. So the next step would be determining the MCP, or the specific heat of each of the components of the flue gas. So remember, in our given, refer to the first problem. So this is the composition of the flue gas in percentage. So we assume that there's 100 moles of flue gas. Okay, let me go back to that. Okay, so if you will remember, this is our given. This is in mole percent. So assuming 100 moles of flue gas, okay, that would be our sorry, not that, this one. This is the composition of the flue gas. Okay, 7.14, 4.28, 7.14 for CO2, 4.28 for CO, and so on. So what we have here would actually be not the composition of the flue gas, but the MCP readings using the graph that I gave you. So these are values that that you can read off from the graph. So this would be at 300 degrees Fahrenheit. Okay. This column is for 600 degrees Fahrenheit, 900, 1200, and 1500. So these are MCP values. And you have to do the same for the cooling air stream. So these are the MCPs of the cooling air or cold working fluid stream. The next step is to calculate the NMCP-dt. So we already evaluated the T minus 60. So those are the temperatures minus the reference temperature. And we multiply now the composition of the flue gas with the MCP that we gathered from earlier from the chart, from the graph, multiplied by the delta T. So we do that one by one for each of the components. So this is for CO2, CO, O2, N2, and H2O. Okay? So this is for the hot flue gas. And you have to do the same for the cold fluid or working fluid. So again, how did we get this? This is for O2 and this is for N2. Okay, so if you will remember, for N2, it's already given. It's the same as the one that entered, since we assumed 100 moles of flue gas, okay, so we calculated the amount of O2 using the molar ratio of N2 and O2. Okay. So again, we have to evaluate the NMCP delta T for each of the component of the air stream. Okay, so this is the component, okay, multiplied by the MCP and dt. Okay. So just like in the parallel flow heat exchanger, we have to get the summation. So for the flue gas stream, this is the summation of the values earlier of the MCPDT value. So summation of this one at 300 degrees Celsius, that would be this value, okay, and so forth. So you have to do the same for the rest of the temperatures that you assumed. And for the cold fluid or the working fluid stream, you have to do the same. You have to get the summation. So this value for 300 degrees Fahrenheit, this is a summation of the NMCP-dt for O2 and N2. Okay. So the next step would be plotting the graphs. So let me open Excel. Oops, this is my thesis. Okay. So first let me type in the different reference temperatures. Okay. And then this is for the hot flue gas. Let me copy and paste the summation of the MCPDT at the different temperatures. Okay. And then next, this is for the fluid or the air, the working fluid. Okay. Right. So we insert a chart. Let me check that. Select data. Remove. We add a new one. This is for the flue gas first. X values would be the Q values, so the heat values, and the Y values would be the temperature. Let's see. Okay. So next we add another one. This one is for the fluid. The X values would be the temperature, and then the Y values would be, nope, wrong. The X values would be the heat, and the Y values would be the temperatures. Okay, so it would look something like this. You have to show the trend lines. Trend lines. Set intercept. This, no, intercept. That one. This is for the flue gas, and then another one. This is for the air. Okay. So going back to the problem, the question would be, if the temperature of the stack gas as it leaves the heat exchanger is 900 degrees Fahrenheit, determine the temperature of the exiting hot air and the amount of heat transferred at this point. Okay, and the percent of the initial sensible heat of the stack gas transferred at this point. So the question would be, for example, from 1500 degrees Celsius, the stack gas or flue gas would leave at 900 degrees Celsius. What would be the heat transferred at this point? What would be the temperature of the cold fluid at this point? And then, what is the percentage of the sensible heat, of the initial sensible heat of the stack gas transferred at this point? Graphically, you can solve it this way. So first is to draw a horizontal line at the initial temperature of the hot flue gas. So this is 1500. So this line is temperature equal to 1500 degrees Fahrenheit. Next is to plot the temperature required, which is 900 degrees Fahrenheit. And from the intersection of both of the lines, this is the intersection of the first horizontal line, you read off the Q value, and you do that the same, the intersection of the horizontal line with the hot flue gas line. So this is, remember, this is our hot flue gas line. You also read the Q value there. But graphically, what you would want to do next is to translate this line to the left. So it should intersect the y-axis as well as the this line, this horizontal line, t equal to 1500. So after doing that, you have to make a vertical line at this intersection. Okay, so that vertical line would help you read the temperature of the cooling fluid. Okay, so this vertical line, this intersection with the cooling fluid line, that would give you the temperature of the working fluid or cooling fluid or cold fluid. Okay, so that is 746 degrees Fahrenheit. Okay. Okay. So as for the value of Q, you have to subtract the readings at this point and then also this point. So that would give you the Q or heat transferred at that point. Okay, at the temperature wherein the stack gas is at 900 degrees Fahrenheit. Okay. So that's the graphical solution. Okay. But of course, if you want to solve that using the equations of the lines, so what you need to do is to, using the equation of the hot flue gas, you input the temperature at 1500 degrees Fahrenheit to solve for Q, and do that again at the temperature 900 degrees Fahrenheit to solve for Q, and then subtract the two values. So let me just do that. Let me try doing that in Excel. So the equation of the this is the equation of the hot flue gas. So that is y is T equal to 0.0012 Q plus 90.873. So if my T is 1500, what is Q? So that is 1500 minus 90.873 divided by, divided by, so this is Q at temperature 1500. So the next one is 900 minus 873, okay, divided by, so you subtract the 2, equals, okay, so is it near? 500. So this one 512,000, that one is 500, but this is more accurate. Okay. So using the equation of lines to solve for small letter T2, so what you have to do is to substitute Q to the equation of the cooling fluid or working fluid line. So that would be equal to 0.0013 times this value plus 85.963. It's different. Let me check the equations. Okay, anyway, you get the idea. But if I substitute, so maybe this one was solved graphically, not using the equation of the lines. Okay, moving on. The next question would be, what would be the percent of initial sensible heat of the stack gas transferred at this point? So the heating value that we got, let's just use the value on the slide, 512,000 BTU. We divide it with the value of the Q at 1500 degrees Celsius. So this value, 1.2 million, was actually obtained here. Okay, so this is the value of, this is the heat at temperature 1500 degrees Celsius of the flue gas. So times 100, we get the percentage. So the next would be to complete the table below. So the table gives you either the temperature of the hot flue gas or cold flue gas, or the heat value. So the first one is, what if the cold air temperature, cooling fluid temperature is 500 degrees Celsius. So, not Celsius, Fahrenheit. Okay. 500 degrees Fahrenheit, you read, okay, so using the equation of the cold fluid or our working fluid, we read at temperature 500 degrees Fahrenheit, directly we can read already the Q. Okay, so this is already Q. But to read the temperature of the hot flue gas, we don't read it by using the intersection of T, small letter T to 500 degrees Fahrenheit with the uh, line of the flue gas. We don't do it that way. So what we do is uh, from the intersection of the line small letter T2 equal to 500 degrees Fahrenheit and intersection with the uh, cold fluid line, we make a vertical line, okay? And with that vertical line, we intersect it with the line, the horizontal line, capital letter T1 equal to 1500 degrees Celsius. Okay, and we make a parallel line. This should be parallel with the uh, hot flue gas line. So, and that this line's intersection with the y-axis would give you the temperature of the hot flue gas. Okay. So how do you solve that? Using the equations of the lines. Okay, so this is how you solve it. Um, anyway, let me move first to the next problem before I show you how to solve it using the equation of the lines. So the next problem, so that is how you solve graphically. The next one is, what if the temperature of the hot flue gas is 1000 degrees Fahrenheit? So what you will do is to make a parallel line with the hot flue gas line. So this line is parallel with this line, and you get the intersection of that line with the horizontal line at 1500 degrees Fahrenheit. You make a vertical line, and the intersection of that vertical line with the cold fluid line, this black line, would give you the temperature of the cold fluid, and you can read Q, okay, also with the intersection of this vertical line with the x-axis. And what if the given is Q, 400,000? So you just read it directly, Q from the x-axis, and its intersection with the cold fluid would give you the cold fluid temperature. And again, its intersection with the horizontal line at 1500 degrees Celsius would help you read the temperature of the hot flue gas line. So again, you have to make a parallel line with the hot flue gas line, and that the intersection of this line with the y-axis would give you the hot flue gas temperature. Okay, so that is the complete table. So how to solve it using the equations of the lines? Let me think first. So if 500 degrees is given, you can substitute 500 degrees in the equation of the cold flue line, cold air or cooling fluid line to read SH. Okay. Next is you make a line, okay, with using 1 point, which is 1500 degrees Fahrenheit in the y value, and x equal to 320,000 BTU, but you use the slope of the hot flue gas. So let me show that. Okay, so first 500. So I want to calculate Q. Okay, I want to calculate Q using the equation of the cold fluid. So this is the equation of cold fluid. So that is 500 minus 85.963 divided by 0.13. Is it near? It's quite near with the graphical solution. Next is I want to make a new line. I want to make this line. So I can do that with one point and slope. That's point slope form. So it's like x minus 318,490. No. Y minus 1,500 minus y equal to x 318,490 minus x, then multiplied by the slope of the hot flue gas line, which is okay. So this is the equation supposedly of this line. Okay. So if I want to get P at x equal to 0, P, so let's replace this with P and then this one with Q. Okay. I want to get P at x equal to 0. So that would be equal to 1,500 minus 318,490 times 0.0012. So it's quite near 1,120 degrees Fahrenheit with the solution using the equations of the line. So you get the idea. Okay. Okay. So the next problem, what's the next question? What is the maximum percentage of the initial sensible heat of the flue gas that can be transferred to the cooling air? Okay. So we can read that by making a vertical line from the intersection of the cooling fluid line or cooling air with the horizontal line at 1000 degrees Fahrenheit. So we read the Q or the SH, sensible heat, at that point, and then we divide it with the SH at 1500 degrees Fahrenheit. Okay, so again, this value was obtained from here. Okay, so this is the SH of the flue gas at 1500 degrees Fahrenheit. Okay, so we divide the two values and get the percentage. So what do you notice? It's bigger than the value, the SH max using parallel flow. Okay. What is the lowest temperature to which the stock gas can be cooled? It's 200 degrees Fahrenheit. So how can you read that from the graph? You make a parallel line with the flue gas line and you shift that line so that one end of the line would intersect with the intersection of the cold fluid line and the horizontal line at 1500 degrees Fahrenheit. So it's like shifting, oops, I cannot edit. Shifting this line here to here, and the intersection with the y-axis would give you the lowest temperature. So how can you do that using the equations of lines. I leave that to you to figure out. And the next question would be, what is the highest temperature to which the air can be heated? It's actually 1500 degrees Fahrenheit. So now you can see the difference with parallel flow heat exchanger. So in parallel flow heat exchanger, the air cannot reach the initial temperature of the flue gas, but for countercurrent heat exchanger, its maximum temperature can be the initial temperature of the flue gas. Of course, it does not really attain that temperature, but it approaches that temperature. Okay, so that ends the lecture on countercurrent heat exchanger.